Hello, today we'll cover part 3 of our series on space-based laser communications. To be more precise, I'll explain the difficulties in getting laser beams through Earth's atmosphere. You already know that laser beams are attenuated by clouds, fog, rain, snow, dust, and smoke, but few people understand how clear air turbulence affects laser beams. Today I'll discuss this. Turbulent eddies in air cause the pressure and temperature distribution to change in time and space. And since the refractive index of air is a function of pressure and temperature, the refractive index distribution also changes in time and space. Finally, since light always bends in the direction of higher refractive index, the beam irradiance at the receiver will be aberrated and vary with time. This is the same effect you see when looking at a star on a clear night. It twinkles. Scientists call this scintillation. In the next image, I show a wave optic simulation of a perfect Gaussian laser beam passing through 10 kilometers of weak, clear air turbulence. The initial beam's cross-section irradiance distribution is shown on the left. A typical refractive index distribution is shown in the middle, and the irradiance distribution at the target or receiver is shown on the right. Note that even weak turbulence dramatically distorts the original beam. This wave optics software propagates the laser beam by solving the wave equation at discrete steps from the source to target, using 10 randomly generated phase plates to simulate the refractive index distributions at various locations. I originally developed this software for laser weapons research, but it can also be used to predict beam propagation from ground to satellites and satellites to ground. You should find it interesting that the beam distortion is different when sending the beam up to a satellite compared to sending it down from a satellite. That's because beam distortion near the source produces more dramatic effects on target. For example, a 10 microradian bend that occurs immediately after leaving the laser produces a 1 meter change in beam position at a receiver 100 kilometers away. I now show an image that illustrates this concept, where a portion of the beam is bent to the left and another portion is bent to the right, resulting in dramatic beam spreading and distortion at the space-based receiver. This distortion at the receiver changes quickly with time. A fraction of a second later, it could be much worse or much better. In the next image, I show a wave optics simulation of this. For this simulation, I used a laser with wavelength equal to 1.55 micrometers and 10 milliwatts output power. The total slant range from ground to receiver satellite was 110 kilometers. The output aperture radius was 1.3 centimeters. And I assumed perfect pointing and tracking with no mechanical jitter transferred to the output beam. This represents the best possible spot on target. The first image shows one instantiation of the beam at the receiver. This receiver's aperture radius was 4 centimeters and is barely visible at the center of the crosshairs. The second image shows how the beam's total power in the bucket, or receiver aperture, changes with different random turbulence distributions. In other words, it gives you an idea of how the optical irradiance changes with time. Note that the average power entering the receiver's aperture was slightly less than 1 microwatt. Now, to be more realistic, I added 30 microradians of random mechanical jitter to the output beam as an angle variation and ran the simulation again. Note the dramatic increase in irradiance variation at the receiver. In some cases, the beam missed the receiver entirely, producing zero power input. This illustrates the need for fine beam stabilization when using lasers for communication. Now, let's consider beams from space to ground. In the next image, I show that you should expect the beam to be distorted less, because the beam passes through turbulence near the receiver only. Next, I show you the wave optics simulation results, assuming a similar beam as before, but a 4 centimeter aperture radius at both the transmitter and receiver. Also, I assumed perfect pointing and no mechanical jitter. In this case, turbulence causes smaller aberrations that appear as speckle. It is a finer interference pattern than we saw at the satellite. Note also that because I used a larger transmitter aperture, the spot size on the ground is smaller. To remove some of the aberrations caused by clear air turbulence, you can monitor the turbulence and use adaptive optics in a feedback loop to correct for it. However, this is complicated and expensive. To learn more about how laser beams propagate through atmosphere and ways to mitigate some of the aberrations, I recommend my book on the subject. It's available on Amazon. If you find this video useful or informative, give it a like, leave comments, and subscribe to the channel. Thank you for watching.